We're surrounded by all these incredibly smart devices. But have you ever really stopped and wondered how they actually see the world around them? How do they sense things like their exact position, or a tiny change in temperature or light?
I mean, think about a simple inkjet printer. That printhead zips back and forth with just insane speed and precision. So how does it know, down to a tiny fraction of a millimeter, where it is at any given second? Well, it's not magic, that's for sure.
The answer, it turns out, is sensors. These are pretty much the unsung heroes of all modern technology. They give our machines the ability to sense the physical world and, actually react to it. So today we're going to dive in and break down exactly how they work.
All right, so let's start with the absolute basics. What even is a sensor? And what is its most fundamental job in any system?
Okay, here's the core idea. At its heart, a sensor is basically a translator. It takes some physical property, like heat or motion or pressure, and it converts it into an electrical language that a machine's brain, its microcontroller, can actually understand.
A really great way to think about it is this. Just like our own senses allow us to interact with our environment, sensors give that exact same power to our devices. They make them aware of their surroundings and even their own internal state.
Okay, so once a sensor has detected something, it needs to report back. And it usually does this in one of two fundamental ways, either digitally or with an analog signal.
Think of it like this. A digital sensor, that's like a light switch. It's binary. It's either on or it's off, 1 or 0. A simple example would be a switch that just checks if a machine's safety guard is closed or not. An analog sensor, on the other hand, is way more like a dimmer switch. It gives you a whole continuous range of values, telling you not just if the light is on, but exactly how bright it is.
And the variety of sensors out there is just incredible. I mean, for pretty much any physical thing you can possibly think of, there's a sensor designed specifically to measure it. Let's look at a couple of really cool examples.
So here's a great example of how you can measure position without anything physically touching. This is called a linear variable differential transformer, or LVDT for short. It uses a moving metal core inside some electromagnetic coils to detect position. And because nothing ever touches or wears out, it's unbelievably reliable and accurate, perfect for those really high-precision jobs.
Now, what about temperature? Well, when you need to measure something crazy hot, you use what's called a thermocouple. It's made of two totally different metals that are joined together at one point. The temperature difference between this hot end and a cold reference end generates this tiny, predictable voltage, which lets us measure a huge range of temperatures with amazing accuracy.
Okay, so we've got all these different types of sensors. But what really makes one sensor better than another one? How do engineers actually judge their performance?
Well, this brings us to a really crucial topic: sensor characteristics. These are basically the key stats that tell us exactly how well a sensor is going to do its job.
Now, in a perfect world, a sensor's response would be this perfect straight line you see on the graph. But, the real world is a bit messier. So we use terms like sensitivity, offset, and linearity to describe how close a real sensor actually gets to this ideal. Let's start with sensitivity.
First up is sensitivity. See that steep line on the graph? That's what high sensitivity looks like. It just means you get a big, easy-to-measure change in the output for even a tiny little change in the input. And for most things, that is exactly what you're looking for.
Next up is linearity, and this one's super important. Ideally, a sensor's output should be perfectly proportional to its input. If you double the temperature, you want the output voltage to double too. So as you can see, the closer its response is to that perfect straight line, the more linear it is. And honestly, the easier it is for us to work with.
Okay, so keeping those ideas of performance in mind, let's look at a brilliantly clever design for a high-performance digital position sensor.
This thing is a great code optical disc. Now, unlike simpler sensors that just count steps, this disc tells a machine its exact, absolute position the second you turn it on. Remember that printer we talked about at the beginning? This is exactly the kind of tech that gives it that incredible precision.
So how does it work? Well, as the disc spins, a bunch of optical sensors read these rings of light and dark bands. Each little slice of the disc has a totally unique binary pattern. It's like a fingerprint for that specific angle. But here is the genius part. The pattern is designed so that when you move from one slice to the very next one, only a single bit of code changes. This super clever design prevents any misreading or errors right at the edges, making the whole system incredibly robust and reliable.
Okay, so we have a sensor and it's putting out a signal. Great. But we're not done yet, not by a long shot. That signal actually has to be interpreted, and this final step is what we call interfacing. And this really is the fundamental challenge, right? The raw electrical signal coming from a sensor is often really weak, it's noisy, frankly, it's a mess. It's essentially speaking a different language than the machine's brain, the microcontroller, and it needs to be translated.
The solution to this problem is a process called signal conditioning, and this is a super crucial step where that raw signal gets all cleaned up. It gets filtered to remove any electrical noise, it gets amplified if it's too weak, and it often gets converted into a format that the microcontroller is actually designed to understand.
So, to wrap it all up, this whole process of interfacing and conditioning is what makes sensors truly useful. It takes that faint, messy whisper from the physical world and turns it into a clear, reliable, digital message that the machine can actually act on. It's what makes the entire system accurate and dependable. You see, sensors are the bridge between the physical and the digital worlds, giving our technology awareness. And as we get better and better at creating these artificial senses, it leaves us with a really fascinating question. What's the next sense we should give to our machines? And what incredible new things will that unlock?